Thanks to Brilliant for sponsoring today's video.
Today we're going to consider the so-called regularization of the product of all natural numbers. In other words, infinity factorial. Of course, it's not really infinity factorial, and it's not really the product of all natural numbers. It's a so-called regularization of that. And in order to really see what that means a little bit more carefully, let's recall how this is done with the sum of all natural numbers, which has been done on YouTube a bunch of different times. In fact, I think I've got a video about it. So, like I said, there are lots of videos and lots of different approaches to showing that the sum of all natural numbers is equal to minus 1 over 12. But that's in really heavy quotes, because clearly the sum of all natural numbers diverges. So what's really going on here is you start with the famous Riemann zeta function, a really important function in analytic number theory. And it's defined as the sum as n goes from 1 to infinity of 1 over n to the s. But of course, by the p-series test, this series converges if and only if the real part of s is bigger than 1. So that means at this line right here, our function zeta of s is only defined on a certain portion of the complex plane. And well, that portion is when the real part is bigger than 1. But what you do is a technique from complex analysis where you extend that function to a larger subset of the complex plane. And that extension will match the original definition where the original definition makes sense. But of course, it doesn't match the original definition where that original definition diverges or doesn't make sense. And so outside of this original region, well, you cannot take this as the definition of the function. You have to take, well, whatever the analytically extended version of the function is. And we're going to see one of those versions today, which was developed in a previous video. And, well, that's exactly how you prove this statement right here. And that's because that extended version has the property that zeta evaluated at minus 1 is equal to minus 1 over 12. But the trick here is you plug minus 1 into the original definition, and then you also plug minus 1 into this extended version, and the extended version gives you minus 1 over 12, and the original version gives you the sum of all natural numbers. But like I was hopefully very clear about, when you move past this region where the original definition makes sense, well, the extension and the original version are not really the same thing. Okay, so anyway, now let's get to what we're trying to do today, which is to try to do something similar with the product of all natural numbers. Okay, so let's start with that. Let's maybe call P equal to this product. So we've got 1 times 2 times 3 times 4 times 5 times 6 times 7, and so on and so forth. But if you're thinking about how to make sense of an infinite product or even a finite product, generally you change that to an infinite sum or a finite sum by applying a logarithm. So let's do that. So if we apply a logarithm, we'll have the natural log of p, that product, is equal to, well, it's going to be the natural log of 1 plus the natural log of 2 plus the natural log of 3 plus the natural log of 4 plus dot, dot, dot. And that's simply because a logarithm changes, well, it's going to change a product into a sum. Okay. Well, what I'd like to very quickly notice is the following, and that is that this thing looks like the following object. So let's look at the limit as s approaches 0 of the natural log of 1 over 1 to the s plus the natural log of 2 over 2 to the s plus the natural log of 3 over 3 to the s, and so on and so forth. In other words, it looks like the limit as s goes to 0 of the sum, as n goes from 1 up to infinity, of the natural log of n over n to the s. But then let's recall something really quick, and that is the following rule for taking the derivative of an exponential function with a base which is not the natural base, and that is the derivative with respect to x of a to the x is equal to the natural log of a times a to the x. Now, that applied to this right here where, well, you're using the chain rule because you actually have n to the minus s, motivates us to observe that this is equal to minus the limit as s goes to infinity, goes to 0 of the derivative with respect to s of the sum as n goes from 1 to infinity of 1 over n to the s. In other words, this seems to be minus the derivative of the zeta function evaluated at 0. So, well, this probably shouldn't be too surprising because when we worked with the sum of natural numbers, we looked at the zeta function. And now when we're looking at the product of natural numbers, it seems like the zeta function is also important. It's just important in a slightly different way. But now from here, we could like exponentiate both sides, and then we would like have our answer. And our answer would be something like this. So 1 times 2 times 3 times 4, so on and so forth. In other words, the number quote unquote infinity factorial, and I'll put this in heavy quotes, is equal to e to the minus zeta prime of s. So, okay, well now that's sorted. We just have to find the derivative of the zeta function evaluated at 0. I should have said 0 before. And you might say, well, where did things go wrong here? Well, things went wrong a lot of different places, like, for instance, pulling this limit outside of the sum, which is most definitely something that happened, pulling this derivative outside of the sum, which is also something that happened, so that there are rules that were broken all over the place. That being said, those rules are almost necessarily broken in this like regularization procedure because clearly we're not having the product of all natural numbers equal to a finite number. So we do have to like cut some corners or break some rules. Okay, so that being said, let's dive into, well, what the value of zeta prime of 0 is.
Hey there, I'd like to take a minute to talk about today's sponsor, Brilliant.org. I've been talking about Brilliant for a long time now, and that's because I truly believe they are a great example how to have fun with learning. Brilliant is where you learn by doing, with thousands of interactive lessons in math, data analysis, programming, and AI. Each lesson comes with hands-on problems so that you can truly learn the material. In fact, it's been proven to help you learn 6 times more effectively than just watching videos. The content is designed by an award-winning team from MIT, Caltech, Duke, Microsoft, Google, and more. Brilliant is also something you can take with you on the go. The mobile app makes it easy to pick the time that works for you. Check out their course library. They have a new range of comprehensive courses in math that's built for learners of any level. Whether you want to brush up on your fundamentals or challenge yourself with advanced concepts, you'll find yourself enhancing your visual and spatial problem-solving skills. But we're scientists here, so don't take my word for it. You should test it for yourself. Treat yourself to a unique hands-on experience by going to brilliant.org/MichaelPenn for a 30-day free trial and 20% off your annual subscription. Thanks once again to Brilliant for sponsoring today's video.
Okay, so we just motivated this notion that the regularization of the product of all natural numbers should be e to the minus zeta prime evaluated at 0, where zeta is the Riemann zeta function, as we talked about over here. And well, in order to prove that, we're going to need to know the zeta function evaluated at 0, and then we can use maybe a nice identity to find its derivative at 0. But let's notice that zeta evaluated at 0 should be equal to minus 1/2. That's the lemma. But if you are not careful again, and you abuse the notation of the difference between the original definition in this region and the extension on a larger region, you have that this means that 1 plus 1 plus 1 plus 1 plus 1 and so on and so forth is equal to minus 1/2, which is another like ridiculous statement. But you know, that's kind of neither here nor there. Okay, so we're going to use an integral representation of the zeta function that we developed in a previous video, and it looks like this. So zeta evaluated at s is going to be 1 over 1 minus 2 to the 1 minus s times the gamma function evaluated at s plus 1 times the integral from 0 up to infinity of sx to the s minus 1 all over e to the x plus 1 dx. Okay, great. And now what we'll do is do a round of integration by parts in order to simplify this. And well, the idea is we want to do integration by parts until when we plug in s equals 0, we'll have 0 in the exponent of x. That's because that'll just turn the x into a 1, and we'll end up with an integral of a rational function where the variable is e to the x, which is easier to deal with. Notice if we've got x's and this rational function in e to the x, that's a big mess. So that motivates the following choices for u and dv for integration by parts. We'll take u to be equal to 1 over e to the x plus 1, or observe that that's going to make du equal to e to the x dx over e to the x plus 1 quantity squared, you know, using the quotient rule or maybe the general power rule and the chain rule, however you want to do that. And then, well, if u is equal to this, then dv needs to be the rest. So we'll take dv to be s x to the s minus 1 dx, which is going to make v equal to x to the s. Okay, great. So there's our integration by parts setup. And maybe I'll leave this like tiny calculation for you, but recall that the integration by parts formula is u times v minus v du. So the u times v part evaluated from 0 to infinity will give us 0. So all we're left with is the integral of v du, but of course that's attached to a minus sign. So that's going to look something like this. We'll have a minus 1 over 1 minus 2 to the 1 minus s, and then we'll have gamma evaluated at s plus 1. And then after that, we'll have our integral from 0 up to infinity of x to the s, e to the x over e to the x plus 1 quantity squared dx. But now what we'll do is evaluate this at 0, and hopefully we'll end up with something that simplifies a bit. So let's see. Zeta evaluated at 0 is now going to be equal to, oh, well, actually, I made a bit of a mistake right here. Notice that this du should have been attached to a minus sign, and that would have canceled out the minus sign that's inside of the integration by parts formula. So my bad. Now, if we evaluate zeta at 0, let's observe that we have 1 minus 2, which is going to give us negative 1. We have gamma of 1, so that's going to give us a minus sign out front. And then we'll have the integral from 0 up to infinity of, we'll have our e to the x over e to the x plus 1 squared dx. Now we just have to evaluate that integral, which is in fact not super tricky. Notice that the derivative of, well, this e to the x plus 1 is in fact in the numerator. So taking the antiderivative here is not too hard. I'm not even going to do a u substitution because I think it's pretty clear. We get 1 over e to the x plus 1. Well, notice that's exactly what we had before, so that should not be too much of a surprise. We need to evaluate that from 0 to infinity. Observe the minus sign got gobbled up in the antiderivative because we moved from a negative 2 exponent to a negative 1 exponent. Now, evaluating this at infinity, well, that's the same thing as taking the limit as x goes to infinity. That's clearly going to give us 0. Evaluating this at 0 is going to give us 1 over 1 plus 1. In other words, it's going to give us a half. That's the lower bound of integration, so that gives us minus 1/2. So there we have it. We've proven this lemma, and now we're ready to move on to the main result. Okay, so we just finished proving this lemma that zeta evaluated at 0 is -1/2. Now we're ready to start calculating zeta prime evaluated at 0. And we're going to use another formula that we developed in a previous video, and that is the following. So we have zeta of s times 1 minus 2 to the 1 minus s. So that should be familiar from something we had before. So this is in fact a descendant or something that precedes the previous formula. Okay, so anyway, this product is equal to the sum as n goes from 1 up to infinity of -1 to the n plus 1 over n to the s. So, this is sometimes called the alternating zeta function or the eta function. So sometimes it has this notation right here. Okay, good. And from here, what we're going to do is take the derivative with respect to s of both sides. So on that left-hand side, well, we're going to have to obviously use the product rule. So that's going to give us zeta prime of s times 1 minus 2 to the 1 minus s. And then after that, we're going to have minus the natural log of 2 times zeta evaluated at s times 2 to the 1 minus s. So that's using some tricky derivative rules, but I think that's okay. And then taking the derivative of this bit, we're going to have the sum as n goes from 1 up to infinity of -1 to the n times the natural log of n all over n to the s. You might say, well, I had a -1 to the n plus 1 before, but one of those signs is going to get gobbled up by the fact that that n to the s is in the denominator. Okay, great. And from here, what we're going to do is evaluate this at 0. So let's send s to 0 and see what we get. So here we're going to have zeta prime of 0, which is in some ways our goal. Here we're going to have 1 minus, well, that's 1 minus 2, so that's a -1. We'll just put the -1 right here. And then we'll have minus natural log of 2 times zeta evaluated at 0 times 2 to the 1 minus 0. So in the end, that's going to give us a plus natural log of 2 because of the cancellation that occurs from zeta of 0 and, well, 2 to the 1. Okay, great. And then, well, what do we have over here? Well, over here, we're going to have this alternating sum of natural logs, but I'm going to write it in kind of a crazy way. I'm going to multiply it by 1/2, and then I'm going to double every term. And now it's going to look like this. We're going to have minus natural log of 1 minus natural log of 1 plus natural log of 2 plus natural log of 2 minus natural log of 3 minus natural log of 3, and so on and so forth. So in fact, what we have is, well, every natural log of an even number is positive. Every natural log of an odd number is attached to a negative. But now what I'm going to do is pull the natural log out of this whole thing. That's going to turn all the differences into quotients, all the sums into products. And then we're going to be left with 1/2 natural log of, so all of our odd numbers are going to be in the denominator, all of our even numbers are going to be in the numerator. And I guess I should say here that we're still breaking a lot of rules, but I think that's par for the course when doing this regularization calculation. So note that we'll have 2 over 1 times 2 over 3 times 4 over 3 times 4 over 5 times 6 over 5 times 6 over 7 times 8 over 7, so on and so forth. So we've got that type of product. But perhaps that product is familiar. In fact, we made a video on this product on the channel before, and it's a typical calculus type homework problem. This is in fact known as the Wallace product. And that's because, well, it's named after the mathematician Wallace, and, well, what its product, it has a product evaluated to pi over 2. So this is going to end up giving us 1/2 natural log of pi over 2. So let's observe what we have here. So, well, what do we have? We've got this expression over here that involves minus zeta prime of 0. And then we've got this thing over here, which has a natural log of pi over 2. So from here, you can solve for zeta prime of 0. Maybe I'll leave that as a tiny homework exercise. We'll start the next board with the value of zeta prime of 0, and then we'll finish this whole thing off. Okay, so solving that equation that we set up on the last board, you end up with the following expression, and that is zeta prime of 0 is minus natural log of the square root of 2 pi. Okay, well, that's cool. And now where can we go from there? Well, from there, we can plug that into, maybe I should say naively, plug that into the equation that we have above, and we'll have our infinity factorial, this is in heavy quotes because it's really a regularization of this, is equal to 1 times 2 times 3 times 4 times 5 times 6 times 7, continued on and on and on, which is the exponential of the negative of this. But the minus signs are going to cancel. The natural log and the e will cancel, and we'll be left with the square root of 2 times pi. And there you have it.